Okay, next get started on chapter 7 about estimates and sample size. This chapter we start on the inferential statistics. And chapter 8 is about hypothesis testing. So those two are the major contents of the inferential statistics. In this section, we will use a sample proportion. I typically use a p-hat represent a sample proportion. Is sample success rate. It's the best point estimate of the population proportion. Population proportion using p, capital letter P, representing the population success rate. So we can use a sample proportion to construct the confidence interval. So this is another major topic in this chapter. It's constructing a sample confidence interval to estimate the true value of the population proportion. We learn how to interpret such confidence intervals, interpreting the confidence intervals. And then also we're going to use formula to find the sample size necessary used to estimate the population proportion. There's the major topics we're going to cover. So the point estimate is a single value. A single numerical value used to approximate the population parameter. So population parameter here, we're talking about population proportion, population mean mu. Those two are the major focus. Population, proportion, and the population mean. Okay, so the sample proportion p-hat is the best point estimate of the population proportion. Okay, so we usually use p-hat to represent the p-hat is representing p. So the Pew Research Center conducted a survey of 1,007 adults, found that 85% of them know what Twitter is. So 85% of them know Twitter. 15% of them do not know Twitter then. Does not know Twitter. Okay, so either know Twitter or do not know Twitter. So the best point estimate of P with p-hat. In this case, p-hat, this is a sample. Survey is a sample of 1,007. So we have the sample proportion here. So 85% is what we call the sample proportion. So sample proportion is the best point estimate of population proportion. So that's why we can say that P must be around 0.85, meaning if you generalize to the entire population, will be 85% of the adults will know Twitter in the US. So the confidence interval is another method. Besides the point estimate, confidence interval is a range values used to estimate the true value of population parameter. Confidence interval is sometimes abbreviated as CI. CI represents confidence interval. Takes first letter of the C, first letter of the interval I, then get CI. Now the confidence interval is a range of values to estimate the true value of population parameter. And this following graph shows you the relationship between the point estimate. This is point estimate. So point estimate gives a single value. And then confidence interval give us entire interval here. So we call this lower limit, left bound is called the lower limit, confidence lower limit. The other one is upper limit on the right hand, upper limit. So the confidence interval have much better chance of capturing the population parameter here, because you have infinitely many values within the interval. So confidence interval has better chance of finding the population parameter. Okay. Compared to the point estimate. Now the confidence level, so that's the difference between the confidence interval and the confidence level. Confidence level is basically the probability is 1 minus alpha. Alpha is what we call the failure rate. 1 minus alpha is success rate. So usually expressed as the equivalent percentage value that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. So the confidence level is also called the degree of confidence. Most common values are 90% confidence level, 95% confidence level, and a 99% confidence level. So 90% confidence level, alpha equal to 0.10. 95% confidence level, alpha equal to 0.05. 99% confidence level, alpha equal to 0.01. Again, they are complement. So if you sum up alpha and then confidence level, it becomes 1. Alpha plus confidence level is equal to 100%. Okay. Let's just show how to interpret this confidence interval. Let's say population proportion p greater than 0.828, less than 0.872. So basically it's saying we are 95% confidence. We have 95% confidence that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion p. Another way of saying this is if you picking a sample of size 1007, constructing the corresponding confidence interval, 95% of the time, 95% of them will actually contain the true value of the population proportion p. So this 95% also refer to success rate of the process being used to estimate the proportion. So the higher the rate, the better it is. So using confidence interval for hypothesis testing, and a confidence interval could be used to test some claim made about the population proportion p. However, it only gives us an informal judgment based on the result. So in chapter 8, we're going to learn a complete new set of method to do the hypothesis testing. But a confidence interval only gives us an informal judgment about any claim or hypothesis. So now let's move on to critical values. The standard z-score could be used to distinguish between the sample statistics that are likely to occur and those that are unlikely to occur. So for example, show the bell curve. If alpha equal to 0.10, that means this is 90% confidence level. So right here, on the two tails, on both tails, 0.10, each tail will occupy alpha over 2. Alpha over 2. Okay, alpha over 2 is equal to 0.05. It's equal to 0.05. 1 minus alpha, that's located in center, which is 90%. So that's 0.90. Okay. So on the two tail there, those are the unlikely event So again, this is unlikely. On this tail is unlikely. And anything in between, that's likely. Okay. Likely event. So this is how you associating the alpha and the confidence level in the bell curve. So under certain conditions, sampling distribution of the sample proportion could be approximated by the normal distribution. So using normal distribution to approximate whatever distribution presented. A z-score associated with the sample proportion has a probability alpha over 2, 40 in the right tail and also on the left tail. So the z-score separated in the right tail region is denoted by z alpha over 2. So this is what we call the critical value or critical z-score. You can easily find it from the table A2, right? On the bottom right-hand corner of the second page, and you'll be able to find those common critical values. So this is likely to occur. On the left tail, that's unlikely to occur. The events are unlikely to occur. On the right tail, similarly, it's unlikely to occur. Okay. So z-score is like critical z-score is used to separate those usual events from unusual events. Unusual events are unlikely to occur. So critical value is a single number on the borderline separating sample statistics likely to occur from those that are unlikely to occur. Number z alpha over 2 is a critical value with the property that separates area alpha over 2 in the right tail of the standard normal distribution. Again, one more time, if you draw this 1 minus alpha in the middle, alpha over 2 on the right tail, and then alpha over 2 on the left tail. Okay. And the critical z-score located on the right tail, z alpha over 2. Now, confidence level 95%, middle, that also give us usual events. And then unusual events occurring on both tails, unusual. Events. The right tail and left tail. And if confidence level 95%, then error in each tail will be 0.025, which is alpha, which is 5% by 2. That becomes 2.5%. 2.5% is 0.025. Okay. And those two are called critical values. We have a positive 1, 1.96, negative 1, negative 1.96. And you can easily find it from table E2. On the second page, bottom right hand corner. And this is common critical values. When there's a 90% confidence, then alpha equals 0.10, critical value is 1.645. There's 95% confidence, then alpha equals 5%, which is 0.05, critical value is 1.96. And confidence level equal 99%, alpha equal 0.01, critical value is 2.575. Data from the simple random sample are used to estimate population proportion, the margin error. You can also call that maximum error allowed. maximum error allowed. This margin error we're using capital letter E. It's a maximum likely difference between the observed sample proportion p hat and true value of the population proportion p. So margin error equal to maximum likely difference between the p minus p hat. Okay. The margin error is also called the maximum error of the estimate. Could be found multiplied by the critical values and divided by standard deviation of sample proportions. Okay. Here p hat represents the sample proportion or the sample success rate. Q hat is equal 1 minus p hat. We call this sample failure rate. M represents the sample size. Z alpha over 2, that's a critical value. Positive 1, positive critical value. Okay, so that's the formula we use to calculate the margin error. Alright, so P, population proportion, it's capital letter P. You can also say that population success rate P has sample proportion, so the sample success rate. For that Twitter example, will be knowing Twitter will be the success event. Not knowing Twitter is a failure event. M represent number of sample size, the number of sample values. E is margin error. Z alpha over 2, critical value, critical z-score, right? Okay. Now the requirement to construct a confidence interval for estimating population proportion P. The sample must be a simple random sample to guarantee its randomly selected object. Conditions for the binomial distribution are satisfied. Fixed number of trials. First condition, trials are independent. There are outcomes in two categories. We call this success or failure event. Probability of success or failure remain constant. Okay. That same condition as when we talk about a binomial probability distribution. So the third condition is at least 5 successes and 5 failures. Okay. So remember that when constructing the sample, construct the confidence interval to estimate the population proportion P. Check 3 conditions before we proceed. And this is a formula. Again, start with the margin error. You need to find the margin error first. And after that, we form the confidence interval. Right? Using p hat minus e, that's what we call the lower limit. And here, this is what we call the upper limit. That forms the confidence interval and eventually contain the population proportion P in it. And there's a couple other ways of writing the confidence interval. You can write P hat plus minus margin error. You can also put in the interval notation, open parentheses, P hat minus E, comma, P hat plus E, close parentheses. And also running rules for confidence interval estimate of population proportion P, confidence level limits for population proportion P. We run 3 significant digits. Right? And for example, like something like 0.235, right? That's 3 significant digits. Okay. Our procedure for constructing the confidence interval for population proportion P. First of all, verify all the required assumptions are satisfied. First one is a simple random sample. Is a simple random sample. Second one, the condition for binomial distribution is satisfied, and we use a normal distribution to approximate distribution of a sampling proportion. Also, third one is this is successes. NP is number of successes. NQ is the number of failures. Number of successes and number of failures must be greater or equal to 5. Okay, that's the third condition. And after that, we move on to step number 2. We refer to table A2. Find a critical value Z alpha of 2 corresponds to the desired confidence level. Then the third step, evaluate the margin error using the formula critical z-score times square root of p hat times q hat over sample size. Now once we know the margin error and then also the sample proportion, then we construct the confidence interval, put in the interval notation. And this is a typical inequality form. So we put into inequality form or confidence or interval notation, like p hat minus margin error, p hat plus margin error. Okay, they are equivalent, and run the result to 3 significant digits. Right, now let's take a look at a concrete example. We know that the Pew Research Center poll of 1007 randomly selected adults show that 85% of the respondents know what Twitter is. So knowing Twitter's success event is what we call success. Do not know Twitter is a failure event. Okay, the sample result n equal to 1007 and p hat is 0.85, because 85% of them know Twitter in this sample, so we know that sample proportion or sample success rate it's 85%, which is 0.85. Now you need to find a margin error that corresponds with 95% confidence level. So since we know 95% confidence level, critical z-score from table A2 is 1.96. Okay. Find a 95% confidence interval, estimate a population proportion P. Based on the result, can we safely conclude that more than 75% of adults know what Twitter is? Assuming that you are a newspaper reporter, write a brief statement to accurately describe the result and includes all of the relevant information. First of all, we check all the requirements. We know it's a simple random sample, so randomly selected, right? So simple random sample checked. Fixed number of trials, we have 1007 trials. Trials are independent because they are randomly selected. And we have 2 outcomes per trial, either no Twitter or do not know Twitter. Probability remain constant. So we check the second one, binomial probability distribution is satisfied. The third condition is number of success and failure both at least 5. How do we know that? We do NP, n times p hat equal 1007 times 85%. That's the number of success. And then that should be approximately, let's write this, 1007 times 0.85. That turned out to be 856 approximately. So we have 856 successes. Number of failures, we do n times q hat. Q hat is 1 minus p hat. So 85% success, then 15% of failures. So it's n times 1 minus p hat. It's 1007 times 15%. Let's see what that is. It's now to be 151 failures, 856 successes. They're both bigger than 5, so we good. So use the formula, find the margin error first. First of all, we know the p hat P hat is 0.85, Q hat is 0.15. Sample size, which is 1007. What else do we need? Critical value, critical z-score equal to 1.96. And we can find the margin error equal to critical z-score times square root of P hat times Q hat over sample size. Okay, so that should be 1.96 times 0.85 multiplied by 0.15 divided by 1007. Then you definitely have to use the calculator to do this and run the result to 3 decimal places. 1.96 times square root of 0.85 times 0.15 divided by 1007. It turned out to be 0.022. That's a margin error. Now once you know the margin error, then we can construct a 95% confidence interval. So all you have to do is plug in the P hat and the margin error. So P hat is 0.85, margin error approximately equal 0.022. So now P hat minus margin error, that's lower limit, and upper limit will be P hat plus margin error. Okay, let's plug in the number 0.85 minus 0.022 less than P plus less than 0.85 adding 0.022. And if you do the calculation, it will be 0.828. The lower limit is 0.828. Upper limit is 0.872. Okay. Then the interpretation of this, based on the confidence interval obtained Part B, it does appear that more than 75% of the adults know what Twitter is, because both of them are bigger than 75%. So definitely 87.2%. Okay. For sure, that's 75% adults who know Twitter is. Because of this, likely to contain true population proportion, and that number definitely is bigger than 0.75, 75%, so we go. Now, the statement summarizes the results. 85% of US adults know what Twitter is. That percentage is based on the Pew Research Center poll of 1,007 randomly selected adults. Okay. In theory, in 95% of such polls, percentage should differ by no more than 2.2 percentage points in either direction from the percentage. 2.2 point is what we call the maximum likely difference between the sample proportion and population proportion. Okay. That will be found by interviewing all adults in the United States. And this is what a newspaper reporter will do. By understanding all these important terms, you'll be able to understand what they try to tell us here. When analyzing the poll, consider the sample should be a simple random sample. Okay, the confidence level should be provided. Usually it's 95%. That's industry convention. Then usually media report neglect to identify that. The sample size should be provided. Should be provided by media, but not always. Except for relative rare case, the quality of poll results depends on the sampling method, the size of the sample. But the size of population is not an important factor. And basically, you can ignore the size of population. Usually, for the general population, the size of population is fairly large. humongous usually. Never follow the common misconception that poll results are unreliable if the sample size is small. Percentage of population size. The population size usually is not a factor in determining the reliability of the poll. Now, suppose we want to collect sample data in order to estimate some population proportion. The question is, how many sample data do we need? How many, meaning you want to estimate the sample size. We could also do that, but before we could do that, let's derive the sample size formula. Determine the sample size, we start with the margin error formula. First of all, we square both side equation, so E square equal to C alpha over 2 times square root of P hat times Q hat over sample size. Square both sides, and then we're gonna get E square and distributed square for each one of this. So we get critical z-score, critical z alpha of 2 square times square, and the square root cancel each other, and we know P hat times Q hat over sample size. And we're going to solve the sample size. We're going to set up proportion. So E square 1 equal to critical z-score alpha, critical z-score square times P hat times Q hat over sample size. Now we're cross multiplying. Now sample E square times sample size equal to critical z-score square times P hat times Q hat. Eventually we divide both sides of the equation by E square. Then we get a margin error formula. So E square cancels sample size equal to critical z-score square times P hat times Q hat over margin error square. Okay. That's how we go from the margin error formula to the sample size formula. And all of these formulas summarized in the formula sheet. You can find all these formulas in the formula sheet. Sample size for estimating proportion P. Sample size equal to critical z-score square times P hat times Q hat over E square when the P hat is known, meaning when P hat is given, or you can calculate the P hat and use this formula. If the P hat is unknown, we use this formula. Critical z-score square times 0.25. If P hat is unknown, then P hat equal to 0.5, Q hat equal to 0.5. That's why P hat times Q hat becomes 0.25. That's why we are using 0.25 here. Okay, and then using P hat equals 0.5, Q hat equals 0.5, we get this is like conservative estimate, which is better off. This is kind of conservative estimate because 0.25 is the maximum value you can get when you multiply P hat times Q hat, and that gives us the biggest value among all of those sample size. The bigger the sample size, the better it is. That's why this is a conservative estimate. Okay, and when you compute the sample size n, it's not a whole number. You always run up to the next whole number, next larger whole number. So many companies are interested in knowing the percent of the adults who buy clothing online. A lot of online retailers, how many adults must be surveyed in order to be 95% confidence that we know that critical z-score is 1.96. Okay. But the sample percentage is in error by no more than 3 percentage point. This tells us we have a margin error. which is 3%. 3%, 0.03. This is maximum error allowed, right? 3% maximum error allowed. Here's a recent result from the Census Bureau. 66% of adults buy clothing online. So this recent survey, so we know in p hat, right? 66%, which is 0.066. 0.66 is p hat, and also we know q hat then. It's 1 minus p hat. 1 minus 0.66 is 0.34. Okay. And this is for pi. Puppy is assuming that we have no prior information suggesting a possible values of proportion. And that means p hat equal 0.5, q hat equal 0.5 to get a conservative estimate. And let's work on part A. P hat, as we just calculate, 0.66. Q hat is complement 0.34. Alpha equal 0.05. Critical z-score is 1.96. Margin error equal to 3 percentage points, which is 3.03. So sample size equal to critical z-score square times p hat times q hat over margin error square. Okay, so this is 1.96 square times 0.66 times 0.34 over 0.03 square. And again, let me get an exact value first, and we run it to the next whole number after that. And this is 957.8389. So no matter what decimal you have, you always run up the next whole number. Remember, the bigger the sample size, the better the result is. So the sample size needed is 958 online shoppers being surveyed. And so to be 95% confident that our sample percentage is within 3 percentage points of the true population proportion P, we should obtain the simple random sample of 958 adults. Okay. And second one, alpha is 0.05, and we know P hat equal to Q hat 0.5. When they are unknown, when P hat is unknown, here the sample proportion is unknown. So margin error should be equal to critical z-score square times 0.25 over 0.03 square. And we write formula first. P hat times Q hat E square. Okay, so this is 1.96 square times 0.5 times 0.5, that's 0.25 divided by 0.03 square. Okay, let's see what that is. And this turned out to be 1,067.111111. And again, we have to run it to next whole number, which is 1,068. So to be 95% confident that sample percentage is within 3 percentage point of true population proportion of all adults, we should obtain a simple random sample of 1,068. And finding the point estimate of margin error from the confidence level. So lower limit, upper limit, that's P hat plus margin error. Adding lower limit is P hat minus margin error. And you're gonna get, you end up with a 2 P hat. Right, when you combine these two, margin error can cancel, so 2 P hat over 2 you get p hat. That's why p hat equal to that. If you do margin error, that's my upper confidence limit is p hat plus margin error minus open parentheses p hat minus margin error. If you expand it, we get p hat plus margin error minus p hat plus margin error. Now we cancel p hat, we get twice of margin error. If you divide that by 2, you get margin error. That's why margin error equals upper limit minus lower limit divided by 2. Okay. That's all for this section.